If you guys want to get started, this is what we're going to do first here is this practice problem from the radical halogenation reaction that we learned last class. I did finally figure out a way to record the lectures. It's kind of ass backwards. I got to put this on this and then record from here, project that on there, whatever. Figured out a way to do it. So I'll post this example when we get done here today. We're really going to do just this one example and then go into the quiz here. I want to make sure everybody's got plenty of time to do the quiz. I don't want that to be like the limiting factor here, all right? So anyway, this is what we're going to start off with this problem here. And again, what we learned is we should be able to do three things. Draw the most stable radical intermediate, draw all the potential products of this reaction, and then using those reactivity values, figure out which one's going to be the major reactor, major product. All right, so again, this is we're going to start off with this example problem from what we learned last class about radical reactions between alkanes and halogens. So the first thing you're going to do is draw me the most stable alkyl radical intermediate. Remember, one of these carbons is going to have that radical electron on them. All right, so one of our carbons in our structure here is going to be the most stable when it has that radical on them compared to the other carbons. So first step is to be able to draw the most stable intermediate there. And then all the potential products. So first of all, what are the type of products that I'm going to get here? What do we call those? So remember what we named those functional groups? So those would be alkyl halides, right? Something with a halogen on them. So all the different products that you could get when you stick a halogen on our alkane here. And then using this chart here, we should be able to determine which one of those is the major product in the reaction. All right, so let's go through it. I'm going to color code these carbons here so we can figure out who we're talking about. That's not very good. All right, so first of all, which one of these carbons is going to form the most stable radical intermediate? What color? Anybody got it? It's going to be this one here, right? The tertiary carbon. Remember, the more carbon-carbon neighbors a carbon has, the more stable the radical. Whoops, where was that? We had this little scale here that showed us that the least stable radicals were those methyl radicals, then primary radicals, then secondary radicals, then tertiary radicals are the most stable. So if you remember in chapter 1, we talked about naming or classifying these carbons as primary, secondary, and tertiary. The reason that we bother doing that is because there's certain differences between them, right? So we'll see trends in stability, in this case in radicals. We'll see more of them as we go throughout the course, okay? And again, what it means to be, for example, a tertiary, so let's just focus on this one. What it means to be a tertiary carbon, that's this one in the middle, is because it's bound to 1, 2, 3 other carbons. Okay? So again, the more carbon-carbon neighbors a carbon has, the more stable the radical that it forms. So in this case, the most stable radical would be when I put that dot on that green carbon. Might look yellow up there, but yeah. That tertiary carbon. Okay, so that's my most stable radical there. All right, so now I got to draw all the products of these reactions. Right, being able to predict products is one of the main things that we're going to need to do with all the different reactions that we learn. In this chapter, we have pretty much just this one as well as the combustion reactions, but those products are always what? For a combustion of an alkane. I get the same two products every time I combust an alkane. CO2 and water, right? So the same two products every time. This is kind of the first real like organic chemistry reaction that we've learned here. So we need to be able to predict the products, right? So to a first approximation, I'm just going to go stick a chlorine on all those different carbons, right? Those are all my different possible products. So I'm going to take that red carbon, stick a chlorine on it. Take that orange carbon, stick a chlorine on it. That green carbon in the middle, which again, it does kind of look yellow up there, but yeah. Stick a chlorine on it. Now, here's where it gets a little bit tricky. I want you to kind of convince yourself, looking at this molecule here, that whether I chose, like basically those two purple carbons right there are identical if I were to put a chlorine on them, right? They would yield the same product because of the symmetry in the molecule. And if I needed to convince myself of that, I could go through and name both of them and I would see that I would come up with the same name. The best way to do it is if you guys have a model kit, which I highly recommend you get because it does just help to look at these things in 3 dimensions. You could see that those two are very much so the same. So then when I draw my product, I would really only have 4. Those 4 there. All right, so we got to know the products of these reactions. Again, this is just going to be putting chlorines on those various carbons. So I'm just going to go through and stick a chlorine on each one of them. All right, I can keep my coloring consistent. All right, so now in order to figure out which one is actually going to be my major product, that's when I need to use that reactivity chart. You gotta do a little math. Okay? How we're gonna calculate this is we're gonna compare for each one of them, we're gonna do the number of hydrogens times that reactivity factor. All right, so let's just do it below each one of these structures here. How many hydrogens were it? So this first structure here, right? I have my chlorine on my red carbon. All right, this first structure here. So how many hydrogens were there originally on that red carbon? 3, right? So it's got 1 bond, so that means if I fill in the rest, that's 3. And is that carbon a primary carbon, a secondary carbon, or a tertiary carbon? Primary, right? It's only got 1 carbon neighbor, so that means that I'm going to use the reactivity factor for a primary carbon, which is 1. So the value I get for that one is 3. Okay? Now I'm going to go on to the orange carbon, right? So this is my next product here. The chlorine's on the orange carbon. How many hydrogens were originally on that orange carbon? 2. Is it a primary, a secondary, or a tertiary carbon? So it's secondary. It's got 2 carbon-carbon neighbors. So I'm going to use the reactivity factor for that, 3.9. That gets me 7.8, I think. Okay, move on. Now I'm at my green carbon. Let me move this up, actually. How many hydrogens were associated with that green carbon, or what looks to be yellow up there? 1. Just 1, right? Again, how do I know how many carbons there are? I'm just going to fill in how many bonds does carbon supposed to have. It's supposed to have 4. So since 3 are pictured, that means that there's 1 hydrogen there. I'm going to multiply that by the reactivity factor. Is this a primary, a secondary, or a tertiary carbon? Tertiary. So I'm going to use that reactivity factor of 5.2. 1 times 5.2 is easy enough to do in our head. 5.2. And the last one. How many hydrogens are there going to be for this particular product here?
Six.
Yeah, nice. So there's 3 on each of these purple carbons. But again, either one of them, if I replaced either one of them with the chlorine, I would get the same product. So that means that I have a total of 6 here to consider. 6 times the reactivity factor. Are these primary, secondary, or tertiary carbons? Primary, they only have one neighbor. So 6 times 1 is 6. So then which one of these would be the major product? Yeah, so I'm going to compare all my calculations here. 3, 7.8, 5.2, and 6. Whichever one gives me the biggest number, that's my major product. So that one there would be the major product of this reaction. All right, so this is a good summary of what we would expect to be able to do from that reaction that we learned, those radical chlorination reactions. Draw the most stable intermediate, figure out how many potential products there are, and then lastly, identify which one of those potential products is our major product. Cool? All right, so you can take a second to copy down this example if you have not already. We're going to go ahead and get started.